Um, this lecture of the workshop is going to be about how to build a reproducible neuroimaging pipeline. Um, it is not necessarily specific to NeuroDesk, but NeuroDesk does make this much easier, and is going to make it so that we can do it pretty simply together today. Now, obviously, you can't, we can't run a whole neuroimaging pipeline today because that takes a day. And so we're just going to simulate the pipeline for the most part, but I've got it set up so that we'll be able to look at the data and the results as we go, and we'll be able to do it together. Um, okay. I also want to mention this workshop has a GitHub website. So whoops. If you just go to github.com/Noah Benson, oh, Benson/VSS 2024. This is a GitHub repository for this workshop. And there's instructions in this README for you to be able to start up your own NeuroDesk instance at home. All you need to do is install Docker. Docker is kind of commercial software that's generally pretty easy to install. Go to docker.com and you can find instructions. It's very easy. But if you haven't installed Docker and you have Docker running, it's basically just 3 commands. You have to clone this repository. You go into the repository directory and then you run docker compose up. Don't do this right now because we got the NeuroDesk instance, but also it would try to download the Docker image, which would take a very long time. But once you're home, or after we turn off the NeuroDesk in a month for this course, you'll be able to use these instructions to do all these tutorials on your own without needing the instance. Yeah. Yeah. To storage, I don't know this NeuroDesk. Yeah.
I hear you.
Yeah, Docker images, in fact, containerization in general takes a lot of space, and that's just the kind of price we pay, unfortunately. So I don't have a good solution for you for that. Sorry. Unfortunately, storage is getting cheaper. Okay. So I just wanted to mention this so you all knew about this later. These tutorials are all in this repository, and once you open NeuroDesk, you'll be able to find them there using that. However, we are instead going to use this NeuroDesk instance today. And I was originally going to have you run a couple commands to start off, but I think I'll give Fernanda some time to get the GitHub addresses into the system before I do that, and I'll start out with just some slides. So I just want to introduce kind of what we're going to do. And I'll just say, by the way, that I would encourage you all to ask questions, especially as I'm going through the tutorial. I'm going to try to do it by live coding, where you just kind of type along with me as I'm entering things into the notebook and the terminal. If we run out of time, I will switch over to copying and pasting things and explaining what they do, because that's just the reality of how this is going to go. If we have extra time, which I don't think we will, then I'll spend a little more time talking about different visual areas. I'll get to that in a little bit. So about this session, this is a series of high-level tutorials on open source reproducible software for handling neuroimaging data. Obviously, I can't teach you everything about everything in an hour. I honestly can't even teach you very much about anything in an hour, but I can get you past that initial hump of not knowing where to start, or not knowing which tool is the right tool, or knowing where to go to kind of find the right tool. So like I said, we're going to try to build an entire MRI reproducible analysis pipeline for a visual experiment together. I mentioned the GitHub repositories for this course are available and have instructions. Okay, so here's what our pipeline is going to look like. Well, here's what a typical pipeline would look like. First of all, you would collect data in an MRI machine. Second of all, you would bidsify the data. If you don't know what bids is, I'm going to tell you in a minute. But bids is basically a format that bids is basically a format that a directory structure format that helps us understand each other's MRI data better. Step 3 would be to run fMRI prep on the data, which will do most of the pre-processing steps. And again, if you haven't heard of this, I will tell you about it in a moment. Step 4 would be to run PRF model on the data. This is another tool for solving population receptive field models. By the way, I didn't mention this, but the visual experiment we're going to be analyzing is a renotopic mapping experiment, because that's pretty much the only experiment I run. And finally, we're going to annotate the data. And by that, I mean, we're going to draw boundaries for visual areas like B1, B2, B3 on the data. Now, realistically, our workflow is going to look like this. We're not going to collect data, and we're in fact not even going to bidsify the data because first of all, we don't have an MRI machine. We don't have time. We can't collect the data. We're going to use an example data set that's publicly available. And then bidsifying the data, I'll talk about this in a minute, but I don't have access to this public data set's original data files, so I can't show you how that would work. But also, putting your data in bids format is typically something you would work with your scan center to do. There's a lot of idiosyncrasies about how scan centers write out files and stuff, and generally speaking, they can help you with this. I'll talk a little more about this in a minute.
Could you please share your
Okay.
screen if that's okay?
So let me start by telling you a little about the data set we're going to be using. So this data set is called the NYU Retinotopy dataset. It's a publicly available dataset on openneuro.org. You can go find it there. It was done with a 3T MRI machine. There were 44 subjects. Every subject participated in at least 2 T1 weighted image scans and at least 6 retinotopy bold scans. We're not going to analyze all that. We're just going to analyze one subject and really just one scan of one subject. But it's enough to give you the idea of how this would work. Okay, so just in case, I realize that not everyone thinks about retinotopy as much as I do, so I'm going to give you a quick introduction. Imagine this is the brain of a subject looking at the screen here, fixating on the white dot. I'm going to get rid of the left hemisphere just to make this a little easier to see. And if we were to put a little stimulus in the left visual field, because this is a right hemisphere, like this, we would see a bunch of blood flow to the back of the brain, the occipital pole back there. And if we then swept that stimulus out to the periphery and back, we would see that this kind of characteristic pattern of blood flow that would flow would kind of move towards the anterior and back towards the posterior as the stimulus moved. So if we then, if I then just take this and plot kind of which part of the visual field does cortex respond to most strongly, it would look like this. So here, what I'm showing you is that this blue region back here responds most strongly to the foveal region here, which is blue. This is called an eccentricity map. It tells us the distance from the center of gaze of the visual field. And then there's an orthogonal measurement where if we were to sweep a stimulus around the visual field, we'll see this kind of orthogonal pattern of activation on the cortical surface. Now this one's a little more complicated because but it's called polar angle, and it looks like this. So here we have the lower visual field represented in red, and we have these kind of stripes on the cortex that respond primarily to the lower visual field. The upper visual field in blue, cyan is kind of along this geostone here. So this is a polar angle map, and these two properties together are how we kind of measure retinal. Oh, I'm sorry, everyone online. I didn't realize I wasn't sharing my screen. You missed some really great animations. Man, can I get this to go away? Well, maybe not. It's okay. Okay. So that's just a quick introduction to what this data set was measuring. So our next step would be to bidsify the data. And let me just tell you a little bit about what BIDS is. So like I said, BIDS is a directory structure kind of file format combination for storing MRI data. It stands for the Brain Imaging Data Structure. It's available. You can find more information about it at this website. It's not just for MRI, it's for all kinds of modalities. It has a lot of really nice features. It's an open standard with self-governance. It lets you track both task data, physiological data, genetic data, behavioral data, metadata, as well as your actual scan data. It's got ways to format all that. And the main reason BIDS was developed is because when you do a scan, you typically get something like this, what's over here out of the scanner, a bunch of DICOM files that are named by numbers or kind of random strings. And if you sent me those to me and asked me to do an analysis for you, I would have no idea how to even interpret those. And so what BIDS is about is turning them into a readable structure over here that someone like me could look at and understand without understanding exactly what scans you ran. It uses very standard file formats, like the Nifty files are the basic kind of unit of the bids structure. And also JSON, tab separated value files, things like that. It just kind of makes data management much easier because it defines the directory structure you need to be using. And a critical thing about bids is that it really enables OpenNeuro, which is, if you don't know about OpenNeuro, it's the website where you can go deposit your MRI data. As long as it's in bids format, they'll take it and they won't charge you for it. And that's great if you want to publish open data sets. And in fact, the NYU Retinotopy data set that we're going to be analyzing, you can find on OpenNeuro. This is what it would look like. You would kind of see the files you could browse. You can download them from here, but it's also available on Amazon's S3. So you can just get it with like the AWS command line or with a tool like DataLad. It just makes sharing data sets very easy. Okay, so I think we're ready to actually start doing some writing some code and stuff, as we're now to the step of fMRI prepping the data. Do we have everyone signed up? Okay, if you are still not to access the instance, yeah, email Fernanda. Okay. All right, so at this point, I'm going to go over to NeuroDesk. And hopefully you have something that looks kind of like this. Obviously, these files are in my directory. They may not be the same for you. But what I want you to start, first of all, is go to the shared directory. And then go to lecture 2. And then go ahead and open this notebook called workflow. You can just double click on it. This is the finished version of the pipeline we're going to build together. And I'm going to keep it open here in case I need to copy and paste code. But we're not actually going to go through this. I just wanted to show it to you and let you know that there's lots and lots of text in here that I am not going to write today, like with you today. That's here to help you understand it later if you come back and want to try to work through it yourself. It also has a lot of information about if you are doing things a little bit differently, if you want to know what website to go to find out more about these kinds of things. It's got a lot of that kind of information. Okay, so once you've got that open, go back to the launcher. If that tab disappeared or anything, you can click this blue plus to make this screen come up again. And what we want to do first is open a terminal. So go ahead and open a terminal. Okay. You probably will start in your home directory. It doesn't really matter where you start, but and that's a little small. I'm going to make this a little bigger. Okay, can everyone see that okay? All right, so we're going to start by typing a command. It's going to go like this. Path in capital letters, please type it exactly as I do, equals, and then in quotes, $path, colon, /home, /Jovian. Jovian is the username that you always have when you're using NeuroDesk. /shared, /scripts, and then an end quotes, and then you can push enter. So it's this line right here that you need to type in. And then once you've typed that, we'll test it by just typing step. And if you've added it correctly, it should give you that message. Yeah. Ooh, that doesn't work. Is that good enough? Yeah, sorry, that's the best I can do without it going off the screen. Okay. So if you typed these commands and you didn't get this syntax error, then raise your hand and we can help you. Oh, awesome. So far, so good. Okay. So this step command is here so that we can simulate the steps that take too long to run. When we get to actually running fMRI prep takes like half a day to run. So this step is going to simulate that for us. What we're going to do now, though, is open up a Jupyter notebook, and we're actually going to compose the entire processing pipeline inside of a Jupyter notebook. And so you can go ahead and push this blue plus again to open up the launcher. And then just pick this first Python 3 IPyKernel option in the notebook section. Oh, hopefully nobody else got that error. You did? Okay. If you got that error, click on this over here. And then try again. Yeah, if you got that error, you need to click on this. The problem was that I had you go to a directory that was write protected, the shared drive. And so you need to click back to your home directory and then you can open a notebook. Yeah. Okay. So this so this notebook is going to be our entire pre-processing pipeline. Now, good practice would be to write lots of documentation in this notebook, but I don't think you're here to watch me write documentation, so we're going to skip that, even though you should do it. And instead, we're just going to like kind of launch right into working on this. So the first thing we want to do is do a little bit of configuration. We're going to kind of tell the notebook where our files are and that kind of stuff. So we're going to start by running from OS import environ. The OS is the operating system module in Python, and environ is basically a dictionary that stores the current process's environment. The environment is a set of variables that's just managed by the operating system. And what's nice about it is you can basically say, I want this particular variable name to be mapped to this particular value, and then any process that you start, like if you launch a new program like fMRI prep will also have access to those environment variables. So this is a useful way to be able to kind of communicate some data or some configuration items across the processes we're going to run. So we're going to start by saying environ of raw data dir. The directory where the raw data is going to be in /home /jovian /shared /lecture02 /data /step0_raw. I'm going to collapse this on mine just so that it's a little easier for you to see it. Okay, and then we're going to say environ of our work directory is going to be /home /jovian /work. We're going to do all of our work on this pipeline in this directory, in the work directory. All right, next we're going to make a directory for our pre-processed data. And we're going to set that to be, we're going to use our work directory and then add a directory called bids to the end. And then we're going to add another one called stimulus file. I think this is the last one. And that's going to be /home /jovian /shared /lec02 /data /stimulus /task-prf _ aperture.nii.gz. I will leave these up here so you can all copy them down. But also, if you miss it, you can always go over to the workflow notebook and find these same under configuration. You can find these same data. Anyway, there they are. And when you've added all these, when you've typed all these lines, you can go ahead and push Shift-Enter, and that will evaluate this cell. It will run this cell, and you can tell it's run because it's now got a little 1 by it. Okay. There's a few other items that are in the actual workflow notebook that are configured there, but we won't need them in this workshop. So they're kind of, if you go review this later, there's explanations there about what they mean. Okay. All right. So we don't have a ton of time, so I'm going to keep moving a little fast, but I'll try to keep these on the screen long enough for everyone to see them. Okay. Next, we're going to say from OS import shader for change directory. And this is because we want to change the directory of our notebook to our work directory so that everything we are doing is in the work directory. So we're just going to run shader and then environ work dir like that. And if it runs and doesn't produce an error, that means it worked fine. If you get an error that says that's not a directory, is that what you got? Okay, I'm sorry. I thought that this directory was there automatically. If you go back to the terminal, just type make dir work. Uh, and for me, it already exists, but if you get a permission denied, type cd to go back to your home directory, and then make dir work. So if you get a permission denied, type cd, and then make dir work. Yeah. Make dir command not found. Wait, and you're in a terminal like this? Did you type, when you typed this path command, is it possible that you didn't include this $ path at the front? Did, uh, I'm not sure why that would have happened. Fernando will try to help you here. Yeah. Oh, I misspelled that, but not really, as long as you're consistent. Yeah. Yeah, thanks for catching that. Okay. Anyone else having issues?
Is there anyone with this problem as well? You have this kind of problem?
No, I just have some.
Okay, so if you're not able to get into the work directory, it's not going to break this tutorial. So I'm just going to keep moving, and if you couldn't get there, that's okay. You can just work in your home directory. Okay, so next we want to create a few directories that we're going to work in. So we're going to start by putting a cell that starts with %bash. That basically means that this cell, instead of being run as Python, is going to run as a shell script. So this will create a little shell script. And just to kind of demonstrate what I meant about the environment, if we have the shell echo $work dir here, it'll echo the value that we set it to up here. And that shows you that the shell knows about this work dir that we just set. However, that's not what we need to run here. What we need to run is we're going to do make dir -p bids to make a bids directory. Make dir -p temp for like where we can store temporary stuff, and then make dir -p config where we can store configuration items. And just run that. It shouldn't produce output. That's correct. Okay. So the next step we have is to load the fMRI module, fMRI prep module. Now, if you aren't using Neurodesk, if you were running fMRI prep on your own, you would probably want to use the fMRI prep Docker. I would refer you to the fMRI prep website. But actually, before we run fMRI prep here, I'm just going to talk a little bit about what fMRI prep is. Yeah. Okay. So fMRI prep is a very general and powerful MRI preprocessing tool. It's one of a community of tools in the NEPREPS community. It's circled here, but there's also MRI prep tools for diffusion and for structural MRI. fMRI prep itself also handles the structural MRI preparation. It automates all of the painful pre-processing steps of MRI, including things like slice time correction and alignment of your structural data with your functional data, and pretty much anything you can imagine, unwarping of the images, that kind of stuff. As I said, it handles both functional and structural MRI and the alignment of them. And it outputs data. It also requires data in BIDS format. And it's one of the tools that works on BIDS. One of the great things about fMRI prep is you run it and it produces these nice reports that show you what it did. So you don't have to go spelunking in your data to figure out whether it worked well on your subject. You just go to a website that it produces and see if the alignments look right and if the data look good. And we'll see an example of that in just a minute. Okay. So we want to run fMRI prep. So on NeuroDesk, we need to import a library called lmod, which lets us load modules in the NeuroDesk environment. And then we type await lmod.load, and we pass it the string fMRI prep /23.2.1. And that's just the module and the version of the software. So you can see here, we run this, and now in our notebook, we have documented the version of fMRI prep we're using. And so anyone who sees this notebook will know exactly what we use to process the data. Okay, so now that we've loaded that, we're going to do another cell that is a shell script. It's going to start with %bash. And just ahead of time, please do not run this cell. It will take a long time. But this is going to be our fMRI prep command. So we're going to run fMRI prep. We're going to pass it our raw data directory as the first argument. And that's basically the input data is there. Then we're going to pass it the preproc directory. That's where we want the data to be, the output data to go, the results of processing the data. And then we're going to put, so our goal here is just to run this on one participant, one subject. So we're going to put as the next argument participants. And that kind of tells fMRI prep how we're going to run this. Now, to make this a little more readable, I'm going to put a backslash and continue this command on the next line. And we're going to provide a few arguments here. The first is going to be the participants label. And we're just going to run the first subject in this data set, which is WL sub 001. Okay, I'm going to continue this line again. And then we're going to put, we're going to tell it what output spaces we want the data in. Now, what this means is when you pre-process functional data, you can you often want to put it in the same space as your T1 weighted image, for example. And so we would just say we want this to come out aligned to the T1 weighted image. And then additionally, there are a lot of other spaces. This is not the only one. What I usually do is SF native, which stands for free surfer native surface. This will project your data on your bowl data onto the cortical surface and just have that as one of the outputs of the fMRI prep process. We're next going to say bold to T1 weighted init header. I'm not going to, because we don't have a lot of time, I'm not going to talk very much about this option, but this has to do with how it figures out how to align the structural and the functional data. And since in this case of this data set, all the subjects basically were scanned for the retinotopic maps and the structural data in the same scan session, we know that the header files for the functional data should basically give us the correct alignment to the structural data, and that's what this option means. But this is kind of in the weeds detail. I just wanted to make sure that when you run this later as an example, perhaps it will work. So that's why I'm including it here. Typically, you would provide a FreeSurfer license file. FreeSurfer is this great structural processing pipeline. It is free, but it does require that you get a license for it. And I didn't have you upload a FreeSurfer license because we aren't actually going to run this and we don't actually need it. But if you run this on your own at some point in the future, you will need it. And there's instructions in the workflow notebook on how to get that up here and use it. And I need another dash there. Okay. We're going to tell it how many processors to use. Is 4. We're going to tell it how much memory it's allowed to use, which is going to be 12 gigabytes. We're going to tell it to do to use as kind of a scratch space or work directory, the directory temp slash fMRI prep. We're going to tell it to skip the bids validation because we already know so typically you would validate that your data set with a properly formatted bids data set before it ran. We already know ours is, so we're not going to worry about that. And finally, we would tell it to be verbose. Now, again, don't run this. But if you want to see what the output looks like, you can go over to the workflow notebook. And there's a cell here that has all the output from when I ran it earlier. And it's pages and pages long. I'm not going to scroll through it. But what we would typically, if we had time, we would just run this now. But instead, we're going to simulate it. So go back over to the terminal. And first of all, we're going to run step 2.0. This is simulating step 0, collecting the data. Now I've already done this, so it's oh, never mind. It's doing it. Okay. So you should see something like this, simulating steps -1 and 0 when you run that. Now, if you weren't able to create a work directory for whatever reason, this may not work, and I'm sorry about that. We can try to debug it later. Yeah. Okay, so now we're going to go ahead and run step 2.1, which will simulate fMRI prep. And I'm going to open up this browser again, just so we can look at what's happening. So I'm going to go into the work directory here, and you see there's a bids directory. And there's basically directories for every subject. And these directories contain the raw data for those subjects. So if I were to go into this directory, for example, there'd be a folder for the session, and then folders for the anatomical data, the field maps, the functional data. You can see there's bold data in here. But additionally, there's a derivatives directory where the results of analyses of these raw data are placed, and there's a source data directory. Now, the source data directory is typically for raw data as well, but in this case, the free surfer outputs, fMRI prep puts free surfer data in the source data directory. And if you look in here, you'll find a free surfer subject for this subject. If you use free surfer, this should be familiar. These are the directories you find in a free surfer directory. I don't have time to go into this in more detail, but I'd be happy to talk about it later if someone is interested to know more about it. Now, because we processed subject 001, there's also an HTML file here for subject 001 that contains the report of their fMRI prep processing. If I just open it here, Jupyter is basically going to say, hey, I don't know how to do fancy websites. This isn't going to work. But fortunately, we're using Neurodesk. So we can go ahead and open up a launcher by clicking on this blue plus. We can open up NeuroDesktop. And if this fails, just try again. This sometimes, I think there's a little hiccup in the pipeline or something. But we can open up NeuroDesktop, go down and open up Firefox. And just go to file : / home / Jovian / work / bids. Oh, yep, thank you. Yeah. Okay, let me try that again. File : / home / Jovian / work / bids / sub -wl subs 001.html. I'll give you a minute to get that down. We can just, once we navigate there, we'll see that this is basically a summary of the fMRI processing. And I'm just going to look through a little bit of this so you get a sense of what's in here. But basically, there's information about what was run. And then there's these great images that show us where it segmented the gray and white matter. So basically, you can look at these, and I realize this is a little blurry. I think it's I think it's because of the projection, not because of the image quality. Basically, this, you can look at this, and if it made a big mistake in the segmentation, you would be able to see it here because the gray matter wouldn't line up with these boundaries. If you scroll a little farther down, there's the surface reconstruction. So this is showing you the surface models of the white matter surface and the gray matter surface. And again, if there was a big error in the surface reconstruction, you'd be able to see it here. There's also information about the field unwarping. They've got these neat little animated GIFs that show you kind of where it had to correct the field inhomogeneities. And we can see that there's some inhomogeneities up here in the frontal cortex, but nobody cares about the frontal cortex, so we're just going to keep going. I'm going to stop there because there's actually a lot in this file, and it's a lot of different information on how this processing pipeline went. But we only have so much time. All right. So that was all it took to fMRI prep the data, ignoring the 12 or so hours it would have had to run that we just skipped. So I kind of wanted to do this just to show you that fMRI prep is not like a monster that you can't deal with. It's actually pretty easy to use if you have the right environment set up. At this point, we're basically ready to go ahead and run a PRF model tool on the data. So let me talk a little bit about population receptive fields and what a PRF model is about. Okay. So neurons we think of as having receptive fields. If you have a population of neurons, like in a voxel, you have a population receptive field. We typically model population receptive fields as Gaussian blobs in the visual field. And the idea is that if this voxel has this particular population receptive field, then when there's stimulus in the middle of the field, it produces a large bold response. Towards the edge of the field, it would produce a smaller one. Out here, it would produce none at all. So it's a pretty straightforward model. As I kind of mentioned earlier, we measured these in terms of polar angle, eccentricity, or distance from center of gaze, and also size, or like a sigma of the Gaussian distribution. So the way that we typically take a retinotopic mapping scan and turn it into a retinotopic map is we take each voxel individually and we look at its bold response. So I'm showing you that down here. This is the bold response for this voxel. And we start with a guess about the population receptive field. So in this particular case, we're going to guess that this population receptive field is down here in the cyan blob. And once we have a guess, we can predict what the bold response would have been because we know what the stimulus was. So here the stimulus is this red bar, and I'm about to show you an animation where the red bar is going to simulate the stimulus that was shown in this experiment. And we'll see the prediction appear down here as it's happening. And what I want you to notice is that every time the red bar sweeps across the cyan blob, immediately after that, you see a spike in bold activity. So I'm going to run that now. So hopefully you can tell that this is a pretty good first guess. This wasn't actually a first guess, but if it had been a bad first guess, we would have adjusted the parameters. We would have moved it around a little bit and changed its size and see if that was a better guess, and we would have kept doing that until we had a good estimate. So that's a kind of high intensity optimization problem that we're solving for each voxel. And there are a lot of oh right, and if you do this for all the voxels, you get these maps I showed you earlier. Yeah. Okay, so there's a lot of tools that actually will solve population receptive field models. Examples are AFNI has a tool for this. There's a Python tool called Popeye, VistaSoft. I'm missing a big one. Analyze PRF. There's quite a few of these. They're pretty much all open source, or most of them are anyway. But one problem I think with them is that none of them are really Dockerized to work anywhere. They're all things you have to install. But there is a Dockerized version of these tools that's called PRF model. And what we're going to do now is go ahead and set up the PRF model Docker to solve these. Now we're running low on time, so I'm actually going to start copying and pasting at this point. And I'm just going to copy and paste some cells over, and then I'm going to explain to you what they do. Apologies, it's generally better for learning if you do this by hand, but we're running low on time. So the first thing we would do is go ahead and build, turn this Dockerize tool into a singularity container. The reason for that is because neuroimage is already inside of a Docker, and you can run singularity in a Docker, but it's hard to run a Docker in a Docker. But there's a very simple command. You can singularity build this Docker image that's named here. And this particular Docker image is called PRF Analyze Vista. It packages up VistaSoft. It includes compiled MATLAB code so that you can run the MATLAB VistaSoft solver inside of a Singularity. Now, I recommend not running this. It actually takes like 10 minutes or something. It's not too bad. For now, I just would not run it. This is the output it produces. It's a fair amount, but not too bad. Okay. The next thing we would do is use another %% command, which will just write a file out to disk. And we just put the contents of the file down here. And we're just going to write out a JSON file that tells us the configuration of the what we want to solve here. So what this has in it is the name of the subject, our subject that we pre-processed was subject 001. The session name that the functional data were collected in is NYU3T01. That's what they called it in this data set. So that's what we're going to put here. Additionally, BIDS has the notion of a task. So every scan you run, there's a task label that gets associated with it. And in this case, PRF for population receptive field was the task that was associated with it. This setting here just tells Analyze PRF, PRF Analyze Vista that this is real data, not synthesized data. We're using the Vista solver, the VistaSoft solver. Additionally, because people tend to run multiple, or people often run multiple PRF analyses, you give it an analysis number. And then you tell it the diameter of the stimulus. And it needs to know that because if it doesn't know how big the stimulus was in the scanner, it doesn't know what the eccentricity is that it's solving for. So you have to tell it how big your stimulus was. Okay. Now, there's a few cells here in the workflow that I'm just going to kind of breeze past. The entire point of these cells is just to take the data that's in BIDS format already and put it in a format that PRF model or PRF Analyze-Vista expects. Basically, these tools they have a particular way they want you to provide the data to them. It's not complicated. It's just a matter of moving some files around. So we're just going to skip over that for now. Okay, and then finally, we would run the PRF model Singularity container. And again, this is just a couple lines of shell script. These first two lines are actually only here because there are default values for some of these Singularity environment variables that we don't want to use that are included in Neurodesk. But after that, we can just basically tell Singularity to run this Singularity image that we built, and it will go ahead. It produces a whole lot of output. It takes about 4 hours or so. And the output is here in the workflow notebook. I want to emphasize that if you come back to this later and you want to try this out, all of this should work for you. This isn't just theoretical. This is all stuff I ran on the Neurodesk instance to get in here. Okay. However, since we're low on time, we're going to kind of leave the PRF model at that, and we're going to go back to the terminal and run step 2.2 to simulate the PRF model results. So this will take just a second, but when it's finished, if you're in the work bids directory, you'll be able to go up to the derivatives folder, and you'll see the PRF prepare was actually the directory that I created with those cells in the workflow notebooks. You can ignore that for now, but there's a directory here for PRF Analyze. I think it actually says PRF Analyze Vista. And if we go in here, there's an analysis 01. There's a subject directory, a session directory, and then here we have a whole bunch of files that came out from this analysis, and they include things like sigma, r squared, which is our kind of measure of confidence for the PRF models. Center x0 and center y0 are the x and y coordinates in the visual field for each voxel, or rather each surface vertex. And all this data basically comes out of a PRF model and is here in standard formats for you to use. Now, I want to point out that let's take the center X not model file. It's a nifty file. However, it contains cortical surface data, and that's because it's basically a nifty file whose volume dimensions are the number of surface vertices by 1 by 1. And that's how you can store surface data in a Nifty file. And that's, since Nifty is kind of the standard for bids, that's part of why that's used there. Okay. So the last thing we're going to do today is actually visualize and annotate this data. All we really need to do for this is, well, okay, let me back up. I'm going to show you a couple slides. So there's lots of tools for, there's actually not lots of tools for annotating data. There's a few tools for annotating data. Afni Summa is one of them. VistaSoft has a built-in way to annotate data. But in general, I find that there aren't really great tools for like drawing ROI boundaries, especially if what you want to do is not draw a boundary, but draw something more complicated. So a while ago, I wrote a tool called Cortex Annotate. It's intended to be a very flexible tool. We wrote it because we were trying to collect lots of annotations from lots of people, and then compare them to see how they compared across raters. And so it's made to be like something where you have other people go check out a GitHub repository and run something and then upload their annotations to GitHub. It also can be run in a much simpler way, which is what we're going to do today. But before we run it, I just wanted to orient you to what you're going to be seeing. So shown here is the left hemisphere of some subject with the red atomic maps, the polar angle maps. And we can inflate it up into a sphere, and then we can take an orthographic projection in order to have like a flattened 2D map of the occipital pole here. So this is the occipital pole right here. And the reason we like to draw on 2D maps, there's tools that will draw on 3D volumes as well, but we like to draw on 2D maps because it makes it very clear where your lines are intersecting with the brain and where they're going. Whereas when you draw on a 3D surface, it's very unclear how 2 points get connected across the cortical surface. That was important for us when we were doing this. It may be less important for you, but we're going to do this on 2D maps today. And again, in case you don't think about the early visual cortex as much as I do, I just wanted to orient you to our subject here. So this is the left hemisphere of the subject we're about to look at. And you can see kind of a representation of the upper visual field along here in cyan and along here, and a representation of the lower visual field kind of here and up here. This is V1, and then V2 and V3 are around it, and I'll just draw some boundaries for you. Basically, if we draw the upper and lower vertical meridians and the horizontal meridian in these maps, it would look kind of like this. And so that's V1, V2, and V3. And I doubt we're going to have time, but if we have time, I'll do a couple more maps as well. Okay. Whoops. All right. So, well, in order to run this tool, we first need to install it. Now, normally I would have you do this in a Conda environment. We didn't really have time to do that. So we're just going to install it locally in the notebook, and just know that next time you come back to this instance, this won't still be installed. You'd have to rerun this cell. But we're going to say pip install cortex annotate equals 0.1.4. So that I add this little bit at the end here because when I'm writing a pre-processing pipeline or something, I always like to document the versions of the software I use. If I had just installed Cortex Annotate, you wouldn't necessarily know what version I used. But go ahead and run that cell, and it'll produce a bunch of output. That's good. That's what it's supposed to do. Basically saying it's installing a bunch of that tool and a bunch of dependencies. And just in case you need to see that still, I'll scroll back up, and I'll just clear that cell output so that you can all see it if you need to type it still. Okay. So now we've installed this Python library, and we can just say from Cortex Annotate import annotate PRFs. That's just a function we're going to call. And so now we can say tool equals annotate PRFs. We're just going to pass it a few arguments. The first is the directory in which the bids data exists. So that's bids. And even if you've navigated away from your work directory over here, that's fine. This notebook is still in your work directory or wherever you started. So we pass it bids. Then we tell it the PRF format. And in this case, it is PRF analyze dash vista. Now we need to tell it what do we want to call the output directory that we put the results of our annotations in. We're going to say derivative equals cortex annotates. We're going to say invert y equals true. The reason for this is because for whatever reason, I think historical reasons, VistaSoft when it solves PRFs, it solves them in terms of the image pixels. So like you start at the top and go down like as like images. The first row is 1 and the next row is 2 and the next row is 3. So it's kind of inverted from the visual field. That's why we have to invert the y. And finally, we're going to say overwrite equals true. And that's only here so that if you come back and run this again on the same directory, it won't give you an error. It basically, if it already sees annotations, it doesn't want to let you overwrite them. Once you've got that typed in, I'm going to collapse this because we needed some space for this tool. But if you run this, oh boy, I misspell it, annotate and notates like that. Okay. This will take just a second to load. And this, by the way, will only work if you ran the step 2.2 to get the PRF data. It'll take just a second to load here, but this is the tool. And we can already see that it's got a list of targets. Basically, this is the subjects we've been looking at and the right hemisphere for them, and this is the left hemisphere for them. And then there's the annotation we want to make. Generally speaking, these are the default annotations, but there's an option to let you pass your own list of annotations. And here we are, ready to annotate V1 on the subject's right hemisphere. Okay, so anyone have trouble getting this open? Okay, great. So we're going to draw these together. I'm going to make this a little bit smaller, just so I can have more of the screen be these maps. And I'm just going to slightly adjust this image slider, the image size slider, to make these a nice size that I can see. Okay, so as I'm looking at this, I think it's pretty clear that V1 is right here. Hopefully everyone can see that. There's representations of the upper visual field in red. Sorry, the lower visual field in red, the upper visual field in cyan. So I'm going to just start by clicking where I think the foveal confluence should go, which is approximately here. Now, it's pretty hard to see, but there's a little dot I put there, and it's in fact so hard to see, I'm going to change the color of that dot to white. Maybe that's a little easier to see. And then I'm just going to start clicking along the boundary that I see here. So when you're annotating visual areas, almost always, or when you're drawing boundaries around visual areas, almost always what you're looking for is a reversal, where you've got something like the upper or the lower visual field in red, and on either side of it is magenta. So there's like a reversal of the polarangle map there, which indicates that you've crossed a boundary into another visual area. Similarly, back here over here in the eccentricity map, you can see that it kind of reproduced the contour on both of these maps. There's also maps down here of the curvature, if you just want to look at the curvature, and of the R squared value or the coefficient of determination. So this is sort of a confidence measure in the maps. So we kind of have followed this boundary here, and we're up to the periphery, and we're going to follow this kind of green color. I know I didn't kind of orient you to these eccentricity maps exactly, but basically the dark color here is the fovea, going up to the green being kind of the periphery. So we're going to follow that green kind of reversal down until we get to the cyan. And then we're going to follow that cyan reversal up back to the fovea. And you don't need to click exactly on the foveal point that you started on. It will close the loop for you. But there's our V1 for this subject. So once you've drawn V1, you can go ahead and select V2 in the annotate menu. Everyone able to use this, or people who are following along? No? Okay. Okay, so when we selected a different annotation, this changed color, and it's actually hard to see now. So I'm going to select, in this style menu, I'm going to select V1, and I'm going to make it black because I think that's a little easier to see. A little bit easier to see. Okay, so we're annotating V2. Now V2 is a little bit harder to draw, I think. It goes, it's sort of halfway between these two representations of the vertical meridian. It follows the horizontal meridian, which is kind of this pinkish color. But again, I'm just gonna, the phobia is very messy. It's almost always messy in random topic maps. I'm gonna do my best to decide where I think the V2 phobia is. Okay, so I didn't place that very well. And so because I kind of screwed it up, I'm gonna push delete, or I think backspace on Windows, and it'll get rid of that point, and I'm just gonna replace it. And then I'm gonna follow what I think is the V2 boundary, which is approximately like this. Yeah. The bottom left map is the R squared. Yeah. Okay, so I've kind of followed this part of V2. And right now, before I talk about how we're going to do the periphery of V2, I'm going to push tab. And it's a little hard to see because the resolution is small, but it basically, there was a circled dot over here, and now this dot is circled, and that means I'm adding to this side of the contour. So now I'm going to kind of follow the same horizontal meridian representation down through here. Okay, so now we're ready to draw the periphery, and I'm going to do something a little weird, which is I'm going to follow this green reversal in the eccentricity map, and then I'm just going to go straight through V1 as if it didn't exist, or as if V2 kind of actually overlapped with V1. And the reason I'm doing that is because when this tool converts these annotations into labels, like it decides where V1 and V2 and V3 are, it will basically in order here say, okay, this is V1. Anything else that overlaps with V1, I'm just going to cut out of that area. And that just makes it a lot easier to draw these boundaries without having to get them exactly lined up with each other. So I'll go ahead and draw this contour up to pretty close to where that point is. And then I'm going to switch to V3. And again, that's hard to see, so I'm going to make V2 a different color. I'm not sure what the best color is, maybe a bright green, or maybe a whitish green. That's pretty good. Okay. So the V3 boundary is a lot like the V1 boundary. We're just going to kind of follow this representation of the vertical meridian. And then we're going to go ahead and again go through V2 and V1. And then we're going to come down here to this representation of the upper vertical meridian and just follow it. And there we have V3. So how am I doing on time? Pretty close. What? Okay. So once we've drawn these, we can go ahead and push this review button. And the idea here is that it's going to prepare a review. It's going to say, here's how I think you've drawn the labels. Here's V1, V2, and V3. And that looks basically right to me. So I'm going to push the save button. Now I could push the edit button, which would go back to editing and let us keep editing. We can actually still keep editing if we push save, but when we push save, it saves them. And it not only saves the, actually, let me show you this. If I go over to the browser, and let me see here. Okay, so I'm going to go to the bids directory. I'm going to go to derivatives, and then there's a Cortex annotate directory now where our annotations are saved. Analysis 01. This is a directory for our subject's right hemisphere. And you can see that there are 3 tab separated files here. These literally just contain the points that you clicked registered to the flattened cortical surface. And then there's a file labels.nai.gz, which again is just a list for every cortical surface vertex. It tells you whether it's in V1, V2, or V3, or none of them. And that's typically what you want when you're doing analyses of like visual areas, is you want a file that tells you the labels of the vertices. Okay, do you mind if I take just a couple more minutes? Okay. So, yeah. Yeah, so in fact, you can edit it right now, and let me just show you that. Okay, so uh, right now, you notice that the white contour is V3. I've got V3 selected, and you can see I'm editing this side of the map, but I can go ahead and like push. Oops, let me make sure I'm on this tool. Okay, you can push delete to get rid of whatever the last point you clicked was. And you can push tab to go to the other side and delete from that side. So you can edit the contours that way. And there's nothing stopping you from pushing review again and resaving it if you didn't like it or editing it further. So yeah, you can absolutely edit these. And since we ran this with overwrite equals true, it'll even let you overwrite the files you've already saved. So yeah. Yeah. Okay. I just really quick want to show you the subject's left hemisphere. This will take just a second to load. And while it's loading, I'm going to say just a little more about this tool. Like I said, this was designed to be very flexible. So the typical way you would use this is you would create a configuration file that had a bunch of information about how to draw these maps. Like basically, our assumption is that not everyone's written a topic mapping experiment or data is the same, and we can't make all those assumptions for you. In the case of this particular in the case of this particular example, we're using a very controlled cases, which is where we ran analyze PRF, so it kind of works. But typically, you would make a configuration file that would tell it how to make the maps and what to draw. And there's examples of that on the website for the tool. All of that is linked from this workflow notebook if you're interested. Yeah.
So you could use this, a different configuration file to load like other localizers.
Absolutely, yeah. So
other kinds of
it was specifically made so that localizers and other kinds of things aside from written topic maps would work. In fact, there's no reason why you couldn't use this to annotate images of anything you wanted. Like it doesn't have to be written topic maps. It's really just a tool for this kind of interface. Yeah. But it comes with a bunch of like neuroscience examples. So
Super.
yeah. Okay. I just wanted to show you this subject's left hemisphere real quick because there's something a little weird about this subject's left hemisphere. You notice that we can kind of see V1 here and V2, but there's sort of this weird shape to the renotopic map. And there's kind of a discontinuity in the V3 boundary. This is something that we see in a lot of retinotopy subjects, and Fernanda, I think, is going to talk a little bit about it. So I thought that would be a nice introduction. Okay. So one last statement. I had originally hoped to get through a lot more visual areas in this example. I obviously had a whole list here. We didn't get through all of them, but I am planning to post tutorials on how to draw all of these areas in the next week or so, and those will appear probably both in the GitHub repository and on our original website when where we'll also post the recordings of this. So if you're interested in that, look out for those. You can also get in touch with me. I've drawn a lot of these areas, and I'm happy to help people with that. But that's really all I have for us to go through right now. Anyone have any questions? Yeah.
Got a question, a favor. I'm asking for a favor. Could you ask them to create the coding parallels?
Ah, yes. Thank you for reminding me. Okay. In preparation, we're going to take a little break here before we start the next session, I think. But before we do the break, there's something that will take a little bit to run that we'll need to do for the next session. Do you want to just come explain how to do that?
Yes.
Do you want to you can use my laptop if you want.
Okay, so if you guys navigate to, oh, sorry guys. So if you guys go on back to your home directory and then shares lecture 3, ESS 2024, this will be our actual repository where all the material will be available. Session 3, and then on session 3 notebook, actually session 3/visualization notebook, you will find a bash script to create your content environment. Sorry. Okay, so I would recommend to just copy each line and paste into a terminal window. And this step will take a little while, like 10 minutes for some reason.
All right, so we're gonna take a little break, about 10 minutes, as long as this takes, probably. So, again, there's snacks in the back, help yourself. Yeah, we'll see you back in, let's see what time it is. So we'll come back, is 45 minutes enough for you? Yeah, yeah, so we'll start again at a quarter after, and finish the last session then. Hey.